Oh, hello there. So, what does this all mean? Well, today we learn the factors of buoyancy and what it contributes to buoyant force. But now let's take a look at this. I just happen to have this with me, so we'll move this Coke out of the way. Now, as you can see, the objects and the boats with the greater volume, for example, SS Anna had 17.91 meters cubed, and the SF Howard had 8.954 meters cubed, and Bessie had 4.477 meters cubed. Bessie had the least volume. Because they had greater volume, it meant that they could hold less weight. Now, when you calculate the net force in total, you can clearly see that Bessie had the least amount of force acting on it, which meant that it could be buoyant longer. And that's buoyancy. In addition, we also know that area was a factor because objects that had the greater area at its base, which would be Bessie, had a smaller height that was folded over. For example, SS Anna had a 4-inch height because we folded 4 inches up, thus making a smaller area at its base. Whereas Bessie, on the other hand, had only a mere 1-inch height that was folded up, meaning it had a much greater base. And that is part and the result to conclusion with the net force being less. But Jim, if you have a 15 by 11.75 inch sheet of aluminum foil, what would be the best dimensions to have on a ship? Can you please explain this?
Alright, given a piece of tinfoil that is length at 15 inches and a width of 11.75 inches, this is how to optimize the carrying capacity of your boat. First you draw a diagram, and we have X's here on the sides because when you cut the paper to fold it up, you don't know the exact height to optimize carrying capacity, so we're solving for X. And we have volume equals length times width times height. So the length is 15 inches minus 2x, because you have the 2x's there, times 11.75 minus 2x, because you have the 2x's there, times x, which is the height. If you distribute that out, you get all of this, and that's continued down here. And then you need to take the derivative of the volume, and that leaves you with 176.25 minus 107x plus 12x squared, and then you set the derivative of the volume equal to 0.
What?
Right, this is our equation from when we set the derivative equal to 0. It's just rearranged in descending order of the degrees of x. And then we use the quadratic equation, which is opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And you plug all of that in, and then you get to the bottom, and you add the square root of 2989 to 107 and divide that by 24, and you get x equals 6.74 inches. And then when you need to subtract, you say 107 minus 54.67 over 24, and then you get x equals 2.18 inches. Alright, and from our last equation we got two x values, and we're just going to plug that into the original volume equation that we set up. And if you plug in 6.74 and you do the math, you come out with a negative number, so that obviously can't be the optimized volume. So if you plug in 2.18 and you do all the work, you get 1.714 times 10 to the first inches cubed. Final results, we plugged in each of the heights of the respective models. And for the Queen Bessie, we plugged in 1 for the height, and we got 4.477 meters cubed after converting from inches. For the SF Howard, we plugged in 2 for the height, and we got 8.954 meters cubed after converting from inches. For the SS Anna, we got 1.791 times 10 to the first meters cubed after converting from inches. And we got that our optimized volume was 4.358 meters cubed after converting from inches. So it makes sense that the closest to the optimized volume was Queen Bessie, and Queen Bessie was the one that held the most weight and was more buoyant.
And that was buoyancy. Buoyancy!